Hello, everyone, and welcome back to the second lecture in this two-part series about the mathematics of encryption. So unlike last lecture, where the focus was on making sure that people who we don't want to read our messages can't read our messages, this lecture is going to be entirely focused on the exact opposite. So we've encountered a message that wasn't intended for us. People don't want us to read it. And so how can we use our knowledge of mathematics to effectively and, more importantly, efficiently make it so that we can read that message? Without further ado, let's go ahead and pop in. The first and most obvious method that we can use when we're deciphering a message is just simple brute force, where we try every single possibility. This is a pretty obvious option for, like last lecture, something like a shift cipher. So let's say, for example, we obtain an encrypted message, which has been encrypted using a substitution cipher, specifically a shift substitution cipher. It's shifted at some unknown distance from the original letter. We don't know how far away, but we know that it has been shifted. And the message that we've received is KW AYRQ YPC RFC ZCQR. Now, we know this is a simple shift cipher. So, if we write out the alphabet, we know that all of these letters are just going to be some distance away from their original position. So we can start by shifting all letters one forward. So in this case, we would have K going to L going to M, and so on. So here we would have that first letter K maps to L, and we get L, W maps to X, and we have LX. Now, already we can go ahead and say that this probably isn't the shift cipher that was used, because LX, this word that we've got first, is not really anything. So we can discount that one and move on to the next possibility. So if they didn't shift it forward, there's also a possibility that they shifted it back. So let's examine that. K shifts back to J, W shifts back to V, and get JV. Now that is an abbreviation for junior varsity, so that might be it. It'd be a little bit unique. A, however, maps backwards to Z, which isn't looking good. Y maps to X, R maps to Q, and we can pretty much abandon it again. Absolutely nothing is going to come from this, so we know that it wasn't that one. Alrighty, well, if they didn't shift it one forward and they didn't shift it one backwards, we can try shifting it two forwards. So now we've got that first letter K goes to M, W goes to Y, already off to a good start, my pretty common word. A goes to C, Y shifts around and goes to A, R goes to T, and we can find the full message quite easily using that. And we find the original message, my cats are the best. And that's not really surprising that we found that that was the message, given that that's just true. We didn't really learn anything from that, but we did find the correct substitution cipher. And so this kind of goes back to what we were talking about in the previous lecture, where we talked about the low number of possible shift ciphers that exist. Specifically, there's only 25. So since we know there's only 25, we can just try all of them incredibly quickly, and we will find very fast which ones work and which ones don't. We can just have a computer generate all 25 possible shifts. And after we've done that, it's just a matter of looking at those and selecting the one that is correct. So very, very simple, not at all challenging. So we can pretty confidently say that, at least in a modern world, a shift cipher is not going to do what we need to in order to figure out the decryption of a message. And an important thing to mention here is the worst case scenario. So what is the worst case scenario in this instance? Well, we tried forward 1, we tried backwards 1, we tried forwards 2. The worst case scenario, the one where it takes the very longest, would be that we try every single possibility which is wrong before we try the one that's right. So in this case, with us alternating like this, it would be if it was exactly in the middle, we would try out all the way until we got to that point, and then that last one that we checked would be it. On average, though, there's 25 possibilities. We would expect it to get that worst case scenario about half the time. So we would expect it on average to take around 12.5, or we'll round up to 13 shift ciphers before we found the proper one. And so in this case, it doesn't matter how long the message is or how many letters are included in it. We just have to check those same 25. So in this case, we would refer to that as a constant time problem. We can solve it in the same amount of time every single time, since there's only those 25 options. So with that knowledge, it's a little bit easier to understand why something like a substitution cipher is a little bit more difficult. In this case, we receive this encrypted message right here. It's much longer, but as we just discussed, that's not at all a problem. We just need to try all of the possible solutions. So let's start with that first letter. That first letter is Z. Well, we can map that to A, and then I we can map to B, and then O, and so on. However, as you can see, this is not going to get us a lot of results. And in fact, it's going to very quickly return a lot of results that aren't valid. And the reason that that is because of the time complexity of this. There's 26 possible substitutions for the first item. There's 25 possible solutions for the second, 24, and so on, which gives us a total of 26 factorial possible considerations, or 4 times 10 to the 26th. So as you can see, this cipher actually has more digits in the possible solutions than there were possible solutions to the previous one. So obviously, we're going to need to work a little bit smarter. Thankfully, we have such a method. First discussed in the 19th century by Arab mathematician Al-Kindi, we've got frequency analysis. Now, frequency analysis is just the observation that certain letters occur more often in the English language than others. Specifically, you'll notice that the letter E very much dominates this graph. So when you're looking at an encrypted message, there's a pretty good chance that the letter that appears most frequently in that message is the letter E. And so if you see a letter that appears more often than any other ones, we can immediately know that, for example, that letter is probably an E in the original message. What's more, if we see a very common combination of letters, if we see KX over and over and over again, we can feel very confident that that's also probably a common letter pair. There's pretty common sequences. In order, it is TH as the most common, then ER, then ON, then AN. Alternatively, if you see the same letter repeated over and over again, if we see YY in a number of places, then we can also feel confident that that's probably another one of those common letter pairs, SS, EE, TT, or FF. And there's actually a very useful site that I'll go ahead and put in the description of this video, as well as the lecture notes for anyone who's following along at home. And that site is a phenomenal tool for frequency analysis. So if we pull that up really quick, it's this site right here. And so what you can do is you can actually put in the message that you have. So in this case, we've got that message that we received. And you can just paste that right on in. And it's done that frequency analysis for us. And so we see there's quite a few possible solutions here, but a couple of them stand out pretty quickly. As we noted earlier, if a letter appears pretty frequently, that letter is probably an E. In this case, by far the most common letter that we have is this 8 right here, or sorry, that T right there. So we can pretty confidently say that that T is probably an E. Additionally, L and Z both appear the second most frequently at 7. However, we can notice that there's a pair of L's in this word right here. And when we consult our frequency analysis chart, we can see that it's pretty common that those letters that appear one after another is probably most frequently SS. So again, we can take advantage of that pattern in the English language, and we can say L probably maps to S, and then we can map Z to the remaining common letter, which is T, since that happens pretty frequently. And then we can substitute that in, and you can see we've already made a pretty significant amount of progress on this message, even though we knew nothing about the original message. We don't know what letters map to what. We just know because it was written in English, there's a certain expectation that can reasonably be maintained. And that site's a really phenomenal learning source that I recommend everybody go and take a look at. Like I said, I've linked it in the description, and I've also included it in the lecture notes. So now that we've got that context, we can see already we're sort of making a lot of progress here. We can continue this process. We can notice that O, Q, F, and S are now all tied with 3 occurrences. And now we can get a little bit more creative with our approach. Specifically, we notice that this word right here becomes some letter followed by an S. We know that it's got to be a vowel. Specifically, it has to be A, I, or U, because the only valid 2-letter words that end in an S are as, is, or us. However, if we note that O maps to A, if we try that substitution, we end up with this somewhat peculiar word here. There's actually only one possible decryption of this word as it stands, and that's the word tease. However, we've already mapped an E somewhere, so we know that that can't be the case. We know that O doesn't map to A. Additionally, we should map it instead to I, because U is pretty uncommon, so we can feel fairly confident that it's one of those. Now we've got the word is there. Now that we've done that, we end up with this right here. And as you've probably noticed, the obvious solution there is that that maps to the word this. So we would take that I maps to H, and we add that substitution in. And we also end up with the word the there, which is very promising. It makes a solid amount of sense that we most likely are going in the right direction. And then we can go ahead and continue the process. So we can take a look at some of the other words that we've got right here. This word in specific, we notice that that's 2 letters right there. Frequency analysis tells us that that is probably going to be FF. So if we map the S to an F, we get this resulting message. However, stiff the something doesn't really make a lot of sense. So if we examine the other possibilities, it actually seems much more likely that that's an L, and that's the word still. All right, now that we've seen that at work, we've got a little bit more headroom. Specifically, we can examine a couple interesting things. This right here is a two-letter word, and this right here is a two-letter word. Both of those must contain a vowel, and it's either got to be a U or an O. U doesn't seem particularly likely, since that right there, F and G, both F and G are on the more common side, where we would expect through frequency analysis that the letter U would perhaps not appear as often. You can see the letter U is very much not a very frequent letter. You'd expect to see it pretty rarely. So we can say pretty confidently that one of those is an O. So if we map an F to an O, we end up with this. That's nonsensical right there, though. EO is not really going to lead us anywhere good. So we can instead say that probably the G is the vowel, that G is the O. And that's looking much better. The only two-letter word that leaps to mind as far as this goes is probably the word no. There's also the word yo, but Y is pretty uncommon as well. And with F occurring 3 times, you wouldn't expect something like a Y to appear like that. And so now we've got much more progress. This word right here, you can see only has a couple valid decryptions. Specifically, it's most likely that decrypts to longer. So we can go ahead and map the U to a G and that K to an R. And at this point, the message is pretty obvious. It's kind of clear where we're going at this point. And so I encourage you, if you've got a minute, pause the video, try to figure this out the rest of the way yourself. In the lecture notes included in the description, I have included a proper solution with the full, complete solution of how we get there. But for now, I'm going to move on to further discussion of the decryption process. So, as you can see, this seemingly impossible decryption was actually managed to very easily be broken by that pretty elegant solution of just examining what letters need to be in order to make sense and what we would expect them to be because we know that the message was written in English. And that actually works in any language, but it'll work for essentially any message that you want if it's the letters themselves that have been changed. So clearly, we see that if we know what method was used to encrypt a message, we have a leg up on knowing how to decrypt it the most efficiently. So most decryption would take place in 2 parts. First, we'd figure out how it was encrypted, and then we would remove that encryption. However, if you recall, many modern encryption methods actually use the exact same modular arithmetic. Obviously, since they all use this same arithmetic, we would have figured out a good way to just quickly remove that, similar to frequency analysis. Well, unfortunately, that's not the case. Remember what we discovered about using a generator. Raising a number to a power and then taking a prime modulus is a one-way function. There is no efficient reversal of that process. So it doesn't matter how long you have. It's simply not going to ever be the case that it is easy to quickly and efficiently determine what resulted in the final message, unless you have the know-how that you would need to in order to remove that encryption. Additionally, frequency analysis won't work because it requires knowledge of what translated letters occur when and where. Most modular encryption, however, takes the character code of the letters and it modifies those themselves. So you take a string of letters, you convert it into some numerical value, and that's what you perform modular arithmetic on. So at the end, you don't actually have a series of letters that you could do frequency analysis on. Instead, you would have the entire string translated into a completely different string with no resulting frequency to analyze. So because it's one way, we have to brute force it. It is the only possible attack that can break modular encryption. However, recall that a generator will create every possible value between 1 and p minus 1. This wasn't particularly impressive when, for example, we had 5 acting as a generator for the number 7. However, for larger prime numbers, that's a little bit more difficult. Specifically, the largest prime number currently known is 2 to the 82 million and some change minus 1. A number which is over 20 digits long. That's an intensely large number of possibilities that need to be tried before you could end up with the solution. Additionally, the method that we went over in the previous lecture was the Diffie-Hellman key exchange, and that's only one of the possible exchanges. In fact, RSA, a much more common encryption mechanism, actually doesn't need to use primes. You can use pseudo-primes, which are just two numbers which share no common factors, which significantly increases the number of possible things that you would need to try before you end up with a possible solution. So that's really what the strength of modern cryptography is. They don't aim for messages which can't be encrypted. Any message could be easily encrypted if you had enough time. The goal is instead to create problems which are so difficult and have no efficient solution that finding a solution outlasts the value of such an effort. By the time that you figure out what that message says, both the person who sent it and the person who received it are dead, as well as their children and their children's children. And so to fully examine truly how difficult it is to brute force modern encryption, suppose we've received an encrypted message, which was encrypted using the Diffie-Hellman key exchange. It used a 20-digit prime number here. And we actually, in this case, wouldn't even necessarily need a generator because we have plenty enough solutions without needing to examine all of those. However, just for this example, let's assume that we do. Additionally, we can suppose that we have access to the best current computer, specifically the best current processor, which has a clock rate of 6 billion instructions per second. Now let's also pretend that this computer is optimized so that every single instruction is exclusively used to check another possible solution for this problem. How long would it take us to decipher this message in the units of seconds, days, and years? Well, we know that the generator has been used to generate some value between 1 and this 20-digit prime number minus 1, but we don't know what was used. On average, we would expect to need to check half of them because that's roughly the time complexity of brute force attacks, which we would have as this 20-digit number. For the sake of simplicity, we're going to go ahead and simplify that to 4.8 times 10 to the 20th. That's all right, though, because we have a very good computer and we can check 10 to the 9th of those numbers per second. So we have 4.8 times 10 to the 20th numbers, and we are checking 10 to the 9th of those numbers per second. Well, this actually doesn't do us a lot of good because we end up with 4.8 times 10 to the 11th seconds to solve that. So that's quite a few. However, we've got time. There's 86,400 seconds in a day, so we can divide that by 86,400 seconds. And we have quite a few days. And then we can take that number and we can divide it by the 365 days that there are in a year, and we get a total of 15,220 years to correctly find the solution to this message. Now, of course, it is possible that we get lucky and we guess it on the first try or the second try or the third try. However, many modern encryption algorithms take this into account, and they intentionally avoid those easy to guess beginning or ending options that would result in not hitting that worst case scenario. So, as you can see, modern encryption doesn't really need to be unbreakable. It just needs to take so long to break that it wouldn't be worth it even if you could. That brings us to the end of this second lecture on the usage of mathematics. As you can see, unfortunately, we have somewhat lost. The first lecture has won in that it has successfully created an algorithm which is so difficult to decrypt that even smart mathematics can't quite seem to crack it. There are some exciting developments in the world of cryptography that would lead to even systems like this being able to be cracked much faster through non-deterministic computing and other exciting developments like that. I highly encourage students to look into that if you are interested. As I said, I've left the link to that site in the description, as well as the complete solution to that problem if you're interested in giving it a go. I hope you enjoyed yourself, and I hope that you have a wonderful rest of your day.